All right, 1.3 exponential functions.
Your screen is frozen.
Oh, thanks. I always forget because I didn't used to do that, but now I have too many people that are like, "What was the homework?" So I just leave it up there, and then I forget that it's frozen. All right, it says to graph the function and state the domain and range. So we have y equals e to the x plus 3, and the plus 3 is like not in the exponent. Turn this off. So an exponential function generically is just kind of like a, I don't even know, like a little curve that like goes up. But with this case, this one has the plus 3, so it would be considered outside the parentheses or whatever, like for how we normally shift things. And so this one is going to shift up 3 units. So just kind of a rough sketch of what we need here. Basically, we would have essentially a vertical asymptote, or horizontal horizontal asymptote at 3 that we're not crossing. And so then basically our graph would come up and actually go through the point 4, because normally it goes through 1. And so it would look something like that. So the domain is going to be all real numbers because it's going out to infinity in both directions. But the range, it can get really close to 3, but it never crosses 3. So we'll have parentheses, 3, all the way up to infinity. And if it's one that you have that you like, say if like the x is negative or whatever, something like that, and it's reflected, you can always do it by plotting points if you're not sure how it shifts. Really with like 3 points you can pretty much draw what it's supposed to look like. 6, this one says to rewrite the exponential expression to have the indicated base. So this is 16 raised to the 3x, and it is base 2. So if we're going to rewrite something as base 2, it basically means turn whatever number we have into a 2, and then what do I need to raise it to in order to make it be what number we had. So I usually will go ahead and rewrite this as 2 to what power is 16?
4.
Yep, so 2 to the 4th, and then I'll go from there and raise it to the 3x. So then we end up with 2 to the 12x for that. Now, if we have it like 8, where it is 1 over 27, all raised to the x. Any idea what I might need to do with that to get, I guess I'll show you, to get it in base 3?
I have a negative exponent.
Yep, negative exponent. So this would be 3 raised to the negative 3, all raised to the x. If you want to just go ahead and do it as 3 to the negative 3x, obviously that's fine too. Use a graph to find the zeros of the function. So this one will need a calculator to plug in the graph to. So 10 is f of x is equal to e to the x minus 4. Well, I guess technically speaking, we may not. Yeah, I guess we would need it.
You want to do that, or I can leave it?
Yeah, if you want to leave it, and I can bring it back to you when I'm done, because we should be done probably in like 10 to 15 minutes, and then.
And where do you want your volleyball cart?
It can just go down in the office. I'm assuming it's in a box.
Yeah.
It can just go down in the athletic office.
Okay.
Because we may take it with us on Friday
Right.
to the tournament. Thank you. I was gonna say we could kind of like plot points to see, but you'd be playing a guessing game because the zeros are on the x-axis, and they're typically going to give you a decimal answer. So we'll just use the calculator for this one. So we'll plug in this equation, the e to the x minus 4, into y equals on our calculator. Let's see if this works. There we go. So e to the x and then minus 4. And then Zoom 6 is standard.
Where's the E button? Oh wait, I see.
Above the ln. So it looks to me like it's crossing the x-axis just at the distance glance. I mean, obviously I could zoom in and see somewhere between 1 and 2, probably about 1.5. But under, if you click second and then the trace button at the top, the second option is 0. And so you'll go to the left of the graph, or in this case under the x-axis, and then you'll go to the right, which is above it, and then it'll ask you to guess, and then it'll tell you that basically the 0 is at 1.39 rounded.
What button was that again?
Second, and then the trace button at the top, and then option 2 is the 0. Did you get it?
Yeah.
Okay. Yeah, we'll do a decent amount with like finding the zeros or the, what are they? Mins and maxes all under that second trace where it's the calc stuff. We'll use a lot of those functions to find things throughout the year. Okay. Jumping down a little bit to the big thing in this section is word problems. I don't necessarily think that they have like the best word problems, so I'm just gonna pick a couple of them. But I do have, I'll print a copy of this growth and decay word problem sheet for you, so that you can have this to like refer to. But basically, these are just some other word problems. I usually tell people to like kind of focus on these and like make sure you understand like where they're coming with these. Or maybe like cover up the answer and like try to work them after like you've done it, like looked over them a little bit, is like studying, because I think these are a little bit better in like the actual problem solving situation of the word problems compared to what they have in the book. But I'll make a copy of those after we finish up today. So 22 is population growth, because that's kind of the most common exponential besides radioactive decay. That's, or like half-life. Those are like kind of the big ones that we do. So 22, I'm not going to write the whole problem, but basically we have a population of Silver Run in the year 1890. So the year 1890 was 6,250. And then it says the population increased at a rate of 2.75% per year. So as a decimal, that would be 0.0275. And then they want us to estimate the population in 1915 and in 1940. So I think we kind of did a couple like this maybe last year briefly, but basically the first year that they give you and they give you information about is going to be your like initial year. So we're going to call this year 0. And then basically we're looking at how many years past 1890 is 1915 and 1940. So this would be year 25 and this would be year, what was that, 50? Because in our formulas that we have, I don't know if this formula was in your notes or not, but P of t is equal to P times 1 plus R raised to the t. And t is like the number of years. So we can't just like plug in the year itself. We have to say like what year number it was. And this P is like our initial amount that we started with. So the 6,250 would be that. So for the year 1915, we're going to have P of t equals 6,250 times 1 plus 0.0275 raised to the 25. And then basically, we'll just use the calculator to get that answer. So we would have that would give us 1,000 or 12,314.76. Now, because we're dealing with population, we can't obviously have a partial person, so we would round to 12,315. Some would argue that you should actually round down because you didn't have a whole person and you can't just like make up 0.24 of a person, but ultimately math rules we're just estimating, so it's not even a obviously exact number. So as long as like it's reasonable, it would be fine. And now obviously even though this is population, so we're dealing with like people, if they told you like if this is more review, so it's probably not going to come up on the exam, but if it were to come up on the exam, they're going to tell you how many decimal places they want things rounded to, and at that point I would just do that, but it'll be kind of the same way that they were with pre-cal last year. And then 1940, we're going to have the exact same thing, but we're just going to replace the 25 with 50. So in 1940, P of t equals 6,250 times 1 plus 0.0275 raised to the 50. So I'm just gonna second entry that, so I'll have to retype the whole thing. And we get 24,200 and I'm gonna go ahead and round 65. Do you know how to like copy down an equation that's already in your calculator so you don't have to do it again? Okay. So instead of, obviously this one wasn't awful to type in, but there are some formulas that are kind of awful. If you hit second and then the enter button, it has a word that says entry above it. It will copy down what you had previously, and then you can go type over whatever you need to type over. So if we wanted to do it like year 75, then I could do that, and it would show me.
Okay.
So it's just kind of nice when you're typing in something that's really long.
Yeah.
Or if you know you typed something in wrong and you're like, I really don't want to rewrite that whole thing, it's just kind of nice for that. So not that you can't, it's just obviously can save you some time. Then part B of this question says approximately when did the population hit 50,000? So now we're working in reverse, basically. We're seeing how many years it would take from the initial year to hit 50,000. And then we'll say what year it is by figuring out how many years that was from the initial year, like what year number we would be in. So we'll replace P of T with 50,000. And then basically leave T blank. Because I'm about to write it in there. And then obviously we can divide by that. We'll have to do a logarithm to solve it. So if we did the 50,000 divided by 6250, oh, that's nice. That actually is 8. I'm going to move the 1.0275 raised to the t to this side is equal to 8. And then I don't know if you remember solving using logs or not, but I do the little L thing. So it would be log base 1.025 raised to the 8 equals t. Do you remember where log base is on your calculator? You need a refresher. Okay. That's fine. So under math, then I usually arrow up because it's faster. Well, it says log base there. So if it's just like a regular common log, obviously we keep the log or the ln button for a natural log. But if we need to change the base, log base will do that. And then we can just type it in. And then of 8. And so this is 84.2, basically. Oh, I missed a number. Hold on. I put 0.025. Hold on. That might change the answer. Whoops. 7.5. Retype this in really quick. 7.5. There we go. Crazy what out to the 100th decimal place can change by like 8 years. So this would be the year, or not the year, it would be 76.7 years in, basically, is when we would hit that. And so it would happen during year 76. So I usually would just specify what year now. Not this, but sometimes they'll say like down to the month, and then obviously we could take this decimal and figure out, okay, you know, what month would 0.65 of a month be, like, of the year?
Yeah.
What month would that put us in? But we don't have to really worry about that. So this would be from, what was our initial year? I don't even remember now. 1890 plus 76. That's 6. 1966. So that would be when the population hits 50,000. So it would take this many years, but this would actually be the year that it's occurring in, basically. Any questions on that one? Let's see, one more of these, and then like I said, I'll give you that other little sheet to look at just for some other examples. 24 is figuring out how long basically it'll take, like if you put like money in the bank and stuff like that. So 24, if John invests $2,300 in a savings account with 6% interest, it's a good interest rate, compounded annually, I know we did stuff last year with it, like being annually, quarterly, monthly, all those things. How long will it take until his account balance has $4,150 in it? So I'm solving for time. So basically the same formula that I was using up here to find t is basically the exact same thing I'm doing here. So I'll have 41,050 is equal to $2,300 that he started with times, it's 1 plus, I'm just going to write 1.06 raised to the t. Did you already type it in and get it?
You get
For your final answer?
No.
Oh. For the dividing
Yeah.
part. Oh, okay. I was like, something might be wrong. You said 1.804?
804.
Okay. Is equal to the well, let me flip it on this other side. 1.06 raised to the t.
Yep.
So then we would have log base 1.06 of 1.804. And you can either, if you rounded this number, you can either use this rounded number, or if you hit second and then the negative button, that takes the answer that you had from the previous thing you found, and it'll plug that exact number in. If you're going out to 3 decimal places, it's really not going to change your answer that much. It's a long time. Although it's basically doubling his money, right? Almost. Guess that's not awful. Put money in there and don't ever touch it. Alrighty, any questions on any of that stuff? Alrighty, so I was like, where did I write down this problem? So problems 1, 5, 9, 21, and 25. There's a few more problems written at the end of this sheet when I make the copy for you. If you want to do more than what I just told you, there's 2 more problems that aren't listed in this that you can do. But that way, just so that you have it. Because the one is a bacteria growth problem. Because that's obviously another one, but that's very similar to the population growth one. Because it's basically